Okay, so let's go ahead and have you guys assign these formal charges. So we have CO, NCl3, BCl3.
I had CO.
You have CO?
Yeah, well, that's one you assigned to me.
Yep. Excellent.
But there's only one, so.
So it's pretty easy, huh?
Well, I tried 3 different ones, and
Okay.
yeah.
I can try the NCl3.
Okay. And who had BCl3? Anyone? Let's see. I have notes here somewhere.
Me.
Oh,
I think it
that's
was
right.
me.
Yes, every time.
Hey, you
Gotta
can't
always
blame
pick on Abby.
you can't blame Abby. She was having massive internet problems last time.
That's true. Did you freeze up, Abby? Did we lose you? And Matt, your formal charges? Okay, good job, Matt. Abby? Your formal charges?
Dr. Henry,
Yep,
could you help me with those? Because I still don't know how to do that.
sure. So I'll tell it to you, but you got to do all the work.
Yeah.
Okay, so formal charges are going to be equals number of valence electrons on
Mhm.
the atom minus number of lone pair electrons not lone pairs, but the lone pair electrons minus number of bonds. Oops. Okay, so for BR, how many valence electrons do we have?
Seven.
Okay.
Oh, where's my-
Okay, how many lone pairs do we have around this BR?
Only one?
One lone pairs electrons, sorry.
Oh, wait. One,
Electrons,
four.
4. And then how many bonds do we have?
6.
Bonds, not bonding
Oh.
electrons, just bonds.
3.
3. Okay, so that equals. And then for Cl, oops, I got carried away. How many valence electrons?
7.
How many lone pair electrons? Around each Cl independently.
Oh. 1, 2, 3, 4, 5, 6.
Okay. And then how many bonds?
3.
Just that one Cl. You want to do one
Oh.
Cl at a time.
There's only one bond.
Okay. Okay, so your formal charges for each of these would be this, each of the Cls are going to be exactly the same. So
Okay.
it's 0, 0, 0, and then 0. Okay,
Okay. So then to find like the formal charges for any single one, like if we have different
atoms,
atoms,
Yep.
we would do this.
that's right. And then that lets us know how stable that structure is, because if your formal charge is like, for instance, this guy has a -1 and a +1, right? This is, it's stable, but not too stable. So carbon monoxide, very reactive, also causes death, okay? One of the reasons why it's very reactive is because it's not as stable as it can be. It exists, but it's not as stable as it can be. If its formal charges was a way of getting to 0, then that would be better. There's no way to make this formal charge is 0. Okay,
Okay.
so
So
So,
stability, oh, sorry, go ahead, Abby.
Oh, sorry. So as long as they equal 0, that means you're stable.
it has stability.
Okay.
It still can be reactive,
Mhm.
but it has stability associated with it. Yeah. And these guys, I mean, it's considered, carbon monoxide is stable, but it's very reactive. It has, because it's at a higher energy level because
Yeah.
of those formal charges. And so the formal charges kind of helps us understand those energy levels. If you have a really obscure energy level, let's say you have a -2 charge and a +2 charge, right? That guy's going to probably be unstable, and it's going to be a high energy. anything that's high energy is going to try to get down to a lower energy. So that means it's going to be reactive. Does that make sense?
Yeah.
Okay, because at the end of the day, it's all about energy, right? So energy plays a huge role in the decisions that these compounds make, right? So you want to try to get to the lowest energy level. You want stability, you know, and if you're high energy, that's not being stable. They kind of go hand in hand. Does that make sense?
Yeah, that makes more sense.
Okay.
Yeah, I've got a question on the one that Cassie had done.
Yep.
So 4 take away 2 take away 3, shouldn't it be 5? Or why is it not 5?
It's
Instead of
4
4.
minus 2 minus 3, right? So that's -5 and a +4. So that's a -1.
But aren't we starting out with
The valence electrons. So carbon has how many valence electrons?
Oh, okay. All right, I get it now. Sorry.
Oh, that's right. Okay. Okay, Selena and Kayla. Selena, can you do thiocyanate? And Kayla, can you do nitrous oxide?
Yep.
Or laughing gas. And do all of the possibilities for the thiocyanate, if you can. Or do the one that's more common, and then we'll talk about the other possibilities, and we'll show why they're not really a possibility. Are you there, Selena?
Yeah, I'm here.
Okay, I just wanted to be sure, you know. How often we'll call on a person, they won't even be there at all, you know, not even showing up on the board.
I don't know. This one's confusing. For me, I don't know why. Yeah, I don't know.
You don't know?
No.
Okay, so let's start off with the number of valence electrons. How many valence electrons do we have for nitrogen?
5.
Okay, so both of those are 5, and oxygen.
6.
So we have a total of
16.
okay. So 16 valence electrons to work with. So if we start off with Okay, so obviously we're going to have a nitrogen in the middle, right? Wouldn't that make sense?
Yeah.
Since it's less electronegative than oxygen.
Mm-hmm.
Okay, so now we get to play with it to see which way can make it so that everybody's octet is full. So if I move this electron over here, we'll have a bond there. Then I move these two electrons here. We'll have a bond here, but that only gives me how many electrons around nitrogen?
6.
6, yeah.
6. So if I move this guy here, so we're taking the 2 from there and then making a bond between nitrogen and oxygen.
Okay.
So that gives me how many around oxygen?
8,
Okay, and then how many around this nitrogen?
6. Or,
2,
sorry,
4.
8.
Okay, but this one has only how many?
6.
Okay, so we want to do a little more maneuvering. How about we move these two between the two nitrogens? Okay, so how many do I have around this nitrogen?
8.
This nitrogen?
8.
And this?
8.
Oxygen. Okay, piece of cake?
Yeah.
So that's one possibility. So another possibility would be my little dots are not showing up very well. So that's 2, 4, 6. Oops. 2, 4, 6, 8, 10, 12, 14, 16. And so that means that this is also another possibility where we have a triple bond over here. Single bond. Okay. You guys see that?
Yeah.
Okay, so we have 3 different possibilities in this situation. Okay, so then we're going to use the formal charges. So let's calculate the formal charges for each of the cases. So for this first one, doing red, so oxygen, what would be the formal charge on the oxygen?
Sorry, can you repeat that? I was doing something.
What would be the formal charges on the oxygen?
So valence electrons, you have 1, 2, 3, 4, 5, 6.
We have 6 valence electrons. How many lone pair electrons?
4.
How many bonds?
2. That would be, yeah.
Okay, and for nitrogen, the
5.
center nitrogen. So we have 5 valence electrons. Number of lone pairs
0.
and number of bonds.
4.
Okay, so that means that this guy would be +1. And then the other nitrogen,
5 valence. 4 lone pairs. And then 2 bonds.
so then that would be a -1. Okay. Sadie, help me with the formal charges for the second possibility. The oxygen,
So
number,
one will be 7.
so, well, the number of valence electrons that oxygen has.
Six.
6, that's correct. That's 6 valence electrons minus the number of lone pair electrons.
1, 2, 3, 4, 5, 6.
Okay. Minus the number of bonds.
1.
Okay. So then that gives us a -1. The nitrogen in the center. So how many valence electrons does nitrogen have?
1, 2, 3, 4.
Valence electrons. So valence electrons are what you're going to find on the periodic table. So if you're counting in that period, count where nitrogen is at. So it'll be 1, 2, 3. Let me pull up my
It'd be
periodic table.
5.
5. That's right. The number of lone pair electrons around the center one.
6.
Lone pair electrons. Do you see any lone pairs up here in the center?
No.
No. So 0, right? And then the number of bonds.
4.
Okay. So then that means that will be +1. And then the nitrogen on the end, number of valence electrons nitrogen has,
5.
number of lone pair electrons,
2.
number of bonds,
3.
so that's 0. Okay. And then the last one I'll do. So the last possibility, so this guy, it has 6 valence electrons, oxygen. It has 2 lone pair electrons, and it has 3 bonds. So then that would be a +1. The nitrogen, the center atom, that would be 5 valence electrons minus 0 lone pair minus 4 bonds, and that would equal +1. And then the other nitrogen,
-2.
yep. So 5 valence electrons minus 6 minus 6 lone pair minus 1 bond. So that would be a -2. I don't know why I put dots there. Okay, that's a +1. Okay, so which one is closest to 0? Or should I say, which two are closest to 0?
The top 2.
The top 2. So we know that the top 2 are probably going to exist. Probably one of the top 2 at least. So we know that this one isn't because this one is far away from 0, right? -2 compared to the other 2. So what is the other rule? Do you guys remember? Who should get the negative charge if we can make it happen?
The one who's more electronegative?
Okay, who is more electronegative?
Oxygen.
Oxygen. So then this would be our,
Oh,
Right.
see the one's 0.
okay?
Right,
So-
because the other oxygen equals 0. So that's why it's not
That's right.
following the
Yeah.
rule.
Okay, does that make sense?
Hmm.
Okay, so let's see, Selena. Good job. Good job. And so nitrogen is more electronegative than sulfur. So nitrogen would be the choice. Okay, so let's see. Oops. So I wanted to show you guys this real quick. Yeah, maybe. Clear. Go back. Okay, so as we talked about, carbon is always the one that's typically in the middle, right? And this basically shows you one of the reasons why carbon is typically in the middle, all right? So in this case, if we did our formal charges, this guy would be a -1, 0, and 0, which Selena basically showed us. Now, in this case, if we had carbon over here, the formal charge would be a -2, kind of throwing things completely off. And then if we had sulfur in the middle, in this situation, then carbon would be a -2, this guy would be a -1, but your sulfur would be a +2, right? Again, it would be so far away from 0 that it's not preferred. The preferred one would be this structure, the one that Selena drew.
So say carbon's not in the question. What determines what's in the middle exactly?
The guy who has the smallest or the smallest electronegativity, the only thing that can't be in the middle is hydrogen, because hydrogen only has one bond that it can make,
Okay.
right? So it'll never be in the middle. Other than that, it's the guy who has the smallest electronegativity.
Okay. Gotcha.
Sometimes you may get exceptions, but for the most part, you don't. Okay. So 99.9% of the time, it's always going to be the guy who has the lowest electronegativity that's going to be in the middle. Okay. Okay, so we talked about those already. And here's an example if we put oxygen in the middle, right? So that one will definitely disobey that rule because you'd have a +2. So it's never really a possibility either. Okay. So here we can predict the structure of nitrate, right? The nitrate ion. So I'm actually going to do this. So this is going to be the center atom.
Nitrogen.
Nitrogen.
Okay. So nitrogen has how many valence electrons?
5.
So nitrogen has 5. So let's do the numbers. So this is 5, and each oxygen has how many?
6.
So 2 times 6.
12.
And then we have
1.
this minus, so we're going to add 1. So that's 18. So we have 18 electrons to work with. So we have nitrogen in the middle. And then we have that additional electron. So we're just going to throw that one on that nitrogen. So that's a total of 6 right now. So, oops. We have oxygen, which has 6 electrons. Let me get a bigger, thicker pen. Is that better? feel like I'm using a crayon. Okay, so what can we do to sit there and make this work? Where are the bonds? Where are we going to move stuff to?
So wouldn't it be a double bond?
Okay, so you're saying move one of these guys over here.
Yeah. Well, two of them on both sides, because then two.
Okay,
Wait. 2, 4, 6. Well, I don't.
oops. And then we had, this doesn't work. Oops.
Okay, I was like, you're missing 2, 4, 6, 8. 2, 4, 6, 8. 16, 18. Yeah.
Okay. So that's one possibility, right? Let's see. So the other one, so this guy would be a resonant structure. Okay, and this brings us to that topic of a resonant structure. What is a resonant structure?
Another possibility?
So it's not really a possibility, it exists. And so technically, so remember, the electrons are moving, right? So they're constantly moving around these atoms. So the ones that are being shared here, they're actually moving around nitrogen. But you're having the ones that are here that are also moving around the nitrogen and the oxygen. Since they're moving, you're going to have this guy that's going to exist, right? And you're going to have this guy that's going to exist. So basically, all you're doing is, instead of having a double bond over here, you're going to have a double bond over here, in this case, on the other side. Okay. So because the electrons are dynamic, you're going to have both of these existing, where this is your first oxygen, that's going to be your second oxygen. So the electron is going to be moving in both cases, both situations. So it's going to be like resonating between the two. Okay. So hence resonant structure. Right? Does that make sense?
Yeah. Is it always off of the original, or is there no like quote unquote original structure? Because they're constantly moving.
Yeah, so really there's no original structure. It's
Okay.
going to be moving between the two possibilities, right?
Okay.
So, and that happens in the case of these guys being exactly the same, right? And having the same type of electron affinity. If they're different, let's say this was sulfur instead of, if it was sulfur, then a sulfur would end up probably being in the middle since it's lower in electronegativity. But but let's say, just in case, sulfur, if this was sulfur, it wouldn't be resonating. It'll actually be a different structure entirely, right? And one would be preferred over the other because oxygen has a stronger electronegativity, so it will be pulling electrons towards it more. So since these guys have the same, they're both oxygen, they have the same electronegativity, they both have the same type of pull. So that means it is going to be resonating between the two. Does that make sense?
Yeah.
It's kind of like you're dating twins, right? And they're exactly the same in both ways. So you want to give them both the same amount of attention. Okay, make sense?
Mm-hmm.
Okay. Okay. Okay, so if we did the formal charges, we'd see that this one kind of works out nicely. Let's do that real quick. Sorry, I had myself. Okay, so we know that this guy isn't going to exist because we're not going to worry about this possibility right here because erase this part here. So we're not going to worry about this guy because we know that center atom is going to be nitrogen. It's going to be the preferred one. And then also we know that because the resonance structure, I mean, not resonance structures, the formal charges. So if we did the formal charges on this oxygen, this very first oxygen, call it O1. So how many valence electrons oxygen has?
6.
How many lone pair electrons?
4. 2.
And then 2 bonds. That'd be a nice 0.
0.
Right? Okay, so what about the nitrogen in the middle?
Nitrogen 0.
So 5 minus 2 minus 3, that's going to equal 0. And then we have the oxygen on the other side.
So -1.
So it would be 6 minus 6 minus 1. So that would be a -1. And that just, if you add these all up together, they will equal the charge of that ion, right? Okay, questions? Concerns? Cash? And so this guy would be preferred because oxygen is more negative, so it wants to have the electron on it. So then it should have that negative charge.
Dr. Henry?
Yep.
So for when you're doing this structure, are you always gonna have to do all possible structures?
So you don't have to do all possible structures. Some of them, like you know, aren't going to exist. Like for instance, we know that this guy isn't going to exist because we know that nitrogen is supposed to be in the middle, right?
Mm-hmm.
But if you're in question, you can sit there and do the formal charges to be sure, right?
Mm-hmm.
Okay, and so sometimes, like for instance, if we did, trying to figure out a way of doing this to make it work, we won't. Double bond, nope, that would give me 5 around here. So if I did, that would just be a resonance structure. So sometimes you'll have options, right? And so let's say, for instance, carbon dioxide. Just trying to think of one on the top of my head. So we could do carbon dioxide like this. Or we can do carbon dioxide like this. 1, 2, 4, 5, 6. 1. Okay, so both of those technically can exist, but one is going to be more preferred than the other, right? And that's going to be based upon formal charges. So if we did the formal charge of this first one, so the oxygen of the top one, so oxygen is 6 valence electrons. It has 4 lone pair electrons, -2, so that one is 0, right? And so we know that this guy's also going to be 0, this oxygen over here, and the carbon
0.
is going to be 0 as well. So it's going to be 4 minus 0 minus 4. Okay, so where this one down here, this oxygen, so I'll call this oxygen 1, it's going to be 6 minus 6 lone pair minus 1 bond. So that should be -1. The carbon is going to be 0. So that's going to be 4 minus 0 minus 4. And then this oxygen here, or oxygen 2, is going to be 6 minus 2 minus 3. So then that's going to be a +1. Okay, so the one that's closest to 0 is going to be the one that you're going to pick because that's more stable. So this would be the structure that you have compared to this structure. Does that make
Okay.
sense?
Yeah.
Okay. Okay, so we talked about the resonance structures. This is one way of drawing the resonance structures, where you just have the two arrows between it. So representing that the double bond could be on either side. Okay, so what is the possible resonance structure of carbon? Carbonate. So who's going to be in the center?
Carbon.
Carbon.
Okay. How many valence electrons does carbon have?
4.
3, 4. So we got 4 for carbon. We have 3 oxygens. So that's 3 times, how many valence electrons does oxygen have?
6, 18.
6. Okay. And then we have an additional 2. Okay, so that's 24. 24 electrons that we're working with. So carbon in the middle. Oxygen here. Oxygen here. And then we have 2 extra electrons. So allows us to have a bond there, and a bond here, but that's only giving us how many around carbon?
6.
So,
Somebody has to be a double bond.
right. So we'll start off with this guy.
So wouldn't there be 3 then possibilities?
That's right. So 2 minus. So the other possibility would be this guy. And then the last possibility would be, or the last resonance structure. Okay, so again, they're all going to exist. The only thing different is that where those double bonds are going to be located. So it's going to shuffle between those oxygens. Make sense?
Yeah.
So Dr. Henry, as long as like they have a negative on top, then we have to put brackets and make sure that our negative is also there with the structure.
That's true, but it's also if it has a positive on top, you should put brackets as well.
Okay.
So any ion?
Yes, any ion.
Okay.
Okay. Okay. Okay, so the next thing that I want to talk about. Okay. So the next thing I want to talk about is strength of the ionic and covalent bonds. Okay. So when we're talking about like the strength of a bond itself, we can actually measure what we call the bond. Okay. And the way that we do that, there's certain values that are already provided. And then, so if we're talking about a compound or a bond between a certain compound, then you'd measure the bond energy of each of the individual bonds. and it's going to be somewhat additive. Now, it's going to give you a ballpark number of how much energy it would take to dissociate that particular bond. And so it lets us know how strong that bond is going to be. Okay, does that make sense? So let me give you an example. So we have, let's say we have a bond between X and Y being whatever you think it is. And this is all based upon the gaseous state in the case of it's being a gas. So the energy that it takes to dissociate X from Y is going to be what we call our bond strength or our bond energy. Okay, does that make sense?
Yeah.
Okay, so again, bond energy is just the energy that's required to break a specific covalent bond of 1 mole of gaseous molecules. Okay, so for instance, if we're looking at H2, sorry for the not putting it subscript, I'll fix that. And we're going to get just 2 hydrogen molecules independently. The energy that's required to break that bond is 436 kilojoules per mole. Okay? Make sense? And you're going to say, where do I get that number, right? So there's a table that's provided in your book, and then also in the back of the appendix, you have the bond energy associated with each of the different bond types. Okay, so in the case of hydrogen and the carbon, each of those bonds are going to be 415, right? So if we wanted to calculate the energy to dissociate the entire thing, it's going to be 416 times 4. So you'd calculate each one and multiply it times 4. Does that make sense?
Mm-hmm.
Okay. So if I have, let's say we have acetate. Let's do something. Let's do methanol. Okay, and I'm breaking it down to hydrogens and oxygen and carbon. Okay, so how would I calculate the energy that's responsible for the dissociation of that?
I think you would find the bond energy between hydrogen and carbon first, right?
Okay, so let's go hydrogen and carbon. Okay, so we have how many bonds that are between hydrogen and carbon?
3.
3. So we'll go 3 times 415. Okay.
1245.
Okay. 1245 kilojoules per mole. And what about, and that's for carbon and hydrogen, or hydrogen and carbon. Okay, what about the carbon and the oxygen?
So that'd be 350, right? Because it's only one.
So we have 1 times 350.
And then 464.
Mole. And then you said between oxygen and
Hydrogen is 464.
hydrogen. Okay, so it's 1 times 464.
So then you just add those all together,
That's right.
and it would yield your 2059 kilojoules per mole.
Okay, piece of cake.
Yeah.
Okay, so what happens if we start talking about double bonds, right? So let's say we had something like this. We have C double bond, C single bond, O, H, and then we'll go single bond, single bond. Okay, so in this case, since this is hydrogen and carbon, that's going to be the same one. So we're going to use those values, right? But here with the double bond has a different energy than just the single bond. So we want to take in consideration that as well too. Okay, so double bond. So this is the bond energy to break up a double bond. Okay, so as the bond energy, as I should say, there's two things that you're going to notice here. So single bond, the bond length is greater than a double bond. So when it's a double bond, it's going to be pulled together a little tighter. If it's triple bond, it's going to be pulled together even more. Does that make sense?
So the closer they are, the more energy they need to
break them. That's right. And then, so, but if you think about it, it's based upon those charges and that sharing, right? So if you're sharing 3 things, you're going to get pulled closer than if you're just sharing 1 thing. Does that make sense?
Mhm.
So your bond length, as bond length decreases, the strength to break that bond is going to increase. It's going to take more energy to break something that's closer together. Okay. So then that allows us to calculate that energy, that dissociation energy, or to calculate the enthalpy change. So the way that we would do that, we would calculate our delta H would be for the entire reaction would be the bond, the energy to break the bond, and then the minus the energy to form the bond. Okay, so for instance, we'd look at the energy to break both of these bonds, so the hydrogen and the chlorine bond. And then we'd look at the energy for the formation of that. Okay, so let me give you an example. So if we go to that table,
Dr. Henry, quick question.
Yep.
Will we be having one of like an example of these in the exam? Will we be able to use this table on the exam?
Yes, this table is going to be provided for you.
Oh, thank God.
Where's the CLs?
HCl.
Oh, duh. I'm thinking, idiot. Never mind.
Okay, oops. ClCl.
432. So there's one of them. There's one bond.
Yep.
So then plus 4. So it's 868.
Although I don't have ClCl up here.
No, that's what I was looking for because it was 2.
Yeah, so I have to look, I have to find out what it is because I don't know it off the top of my head.
Okay.
So let me.
Possibly 868.
Oops. So ClCl is 243 kilojoules per mole. Oops. Okay.
74? 79?
Okay. So in this case, the bond association for the hydrogens was 436. The chlorine is 243. And then,
What? 443.
I'm sorry, no, for the chlorines, it's 243. Chlorine, the chlorine gas.
Yeah, I thought you said 443, so that's what I put
Oh,
in
sorry.
my in my calculator.
Yeah, it's 243.
And then hydrogen.
Okay, so then we're going to add those two together. And then we're going to subtract the formation of the HCl. Okay, and so this is going to give us the total energy that's associated with the formation of this new compound. Does that make sense?
Mm-hmm.
Okay. Okay, so then we just basically divide this number by 2, and then that would give us the enthalpy for a single HCl, since there was 2 of those.
Oh, okay.
Yeah, and that should be for not 2, but it should be for 1. Another typo. Let me fix that. So that's for 1 HCl. Okay. Okay. So in theory, we could sit there and calculate the enthalpy for each individual compound this way by using the bond energy. And it's going to give you a rough estimate because usually it's going to be a little bit higher because the energy that it takes to break bonds, that initial energy sometimes is like for that very first bond to break, usually is a little bit more than what is actually measured. So if it's a big compound, okay. Okay, so we can sit there and do this with these equations as well too, right? And so I'll actually save this for you guys when we meet. I guess we won't meet till next week. So I'll save this for you guys for the next time, or actually to practice on. So for a practice the exam, potentially. Okay. And then the other thing I wanted to talk about is ionic bond strength. So when we're talking about ions, there's energy associated with that too, right? And so the energy that it takes to sit there and break apart that, the way that you would do that calculation. Okay. The way that you would do that calculation is you have what we call the constant. It's just a constant that's depending on the crystal type. So depending on the type of crystalline structure that you make, so there's one that's called, and that'll be given to you. In case it'll tell you which crystal structure that you make. So there's like a face center, there's a body center, And so depending on the crystalline type, it's going to have a constant that's going to be associated with that. And then, so you're just going to have C for that constant. This here represents your charged ions, right? So this is your positively charged ion. This is the negative charge on your negative ion, right? And then this here represents the inter-ionic distance. So basically it's the radius of your positive and your negative charge. So it would be the sum of the radius of both of those. And you're going to ask me, where can you find those? So those can actually be found on. Okay. So when we're talking about these charges, so let's say, for instance, we're talking about magnesium, oxide. So in this case, we're talking about the charge itself. So magnesium has what charge associated with it?
Magnesium's a +2.
Okay, so magnesium will be a +2. And then oxygen is,
-2.
so it's a -2. So in this case, you're going to use 2 and 2, right? Because both of those are going to be this guy. The charge on this guy is always going to be the positive, so it's that value, so it's 2 times 2. Okay, and then you're going to take the distance, which would be the sum of each of the radius of each of those. Let's see if we can get that on P table real quick. Okay, so we had oxygens. Okay, so we have 48. And then magnesium is 145. So we'd add those two together, that 48 plus 145. And then that's going to give you your value. So what is that? 3, 9, 1. So 193. Okay, so then that R naught is going to equal to 193. This is the radius of oxygen. This is the radius of magnesium. So we're just adding them together, and then that's going to give us the radius of magnesium oxide. Or not the radius, but the distance. Okay. Or not of magnesium oxide. Okay, so then you're going to end up with your delta H being whatever the C value is, depending on that lattice, 4C divided by 193 equals. Okay, questions?
And you're given C, right? So that's
Yeah,
why we
so-
don't know that specific.
Yeah,
Okay.
because it would be the lattice. What type of crystal
Whatever.
structure you have.
Okay, whatever
Yeah,
structure.
so that's going to be given to you for this process.
Okay.
And how did you get the radius again? Or was
So
that
the
already
radius you
noted?
can find on P table.
Mm-hmm.
So again, let's see.
And those will be given as well too, right?
I'm going to try to get a little table together for you on that
Okay.
one.
Oh,
So
okay.
it's going to be provided here on P table.
Okay, gotcha.
Okay. So again, so this just basically tells you the ionic bond strength. It lets you know, and it's also what we call the lattice energy that's associated with the lattice. Okay. So if we were working with lithium oxide, this would be the same situation where we have charges are going to be 1. So it'll be just 1 times 1. So it'll just be C over the distance between the two. Okay. Okay. So there's another way of doing, of calculating the energy associated with a chemical equation. And that's basically using the Barn-Haber cycle. And so what you're going to do is you're going to actually break down each of the different components. So in the case of, we have cesium plus fluoride. So both of these guys in this case are going to be starting off as, we have our solid, and then we have fluorine gas. So this here basically is the energy that's associated with changing that cesium from a solid to a gas state. And then that, you can actually find that on the back of your in your appendix, or it'll be given to you on an exam. Then this represents the ionization energy. So basically to go from one guy giving up an electron, and so cesium is going to be giving up an electron to try to get fluorine, induce fluorine to become independent. So, and then here is the energy that's associated with dissociation. So you're getting fluorine to break apart. And so we can calculate that using the what other way. Ionization energy, we can actually find that on P table as well. This here is the electron affinity. So basically the desire for fluorine to become an ion, so take up that ion that cesium was giving up. And then this here is them coming together. So that would be the lattice energy. Okay. So if we go through this process, these guys are going to be added and these guys are going to be subtracted. So these guys are all positive values. These guys are negative values. But if you look at the difference, the overall change, that's going to represent the enthalpy of formation. Okay. So if we go through this process of all of these adding up minus these guys, we're going to end up with negative 553.5 kilojoules.
I feel like that's a lot of steps for error.
Yes, it is. Yeah, so, but it is another way of calculating the process.
Okay.
Okay. Okay, so the next part is geometry, right? So we've talked about bond length, we've kind of talked about bond energy. And so the idea is that ultimately you want to try to have a low energy associated with you in terms of how the molecule is going to form and the structure that it makes. And so one of the ways that it keeps a low energy is by trying to keep as much of a distance between its components, the things that it's attached to, so that they're not interfering with each other. Because if you put electrons, both of those are negatively charged, if you put them close together, they're going to kind of repel each other. That's going to be energy. That's going to cause problems, right? And so you want to try to be as far away from each other as possible. And so this deals with that concept of the valence shell electron pair repulsion. So if you have two electron pairs, they're going to repel each other. So they're going to try to be as far away from each other as possible, as they can possibly be. And so in this part, we're going to actually talk about geometry, molecular geometry. Okay. So the bond angle basically represents the angle between two things that are being bonded together. So for instance, we have carbon and hydrogen bonded here. So the bond angle is the difference, is the angle between this bond here and this bond. Okay. And so that represents our bond angle. The bond length represents the distance between what things are bonded to each other. Okay. Make sense? So this guy is formaldehyde. And so the bond length between here is 118 degrees. Now, the reason why it's 118 degrees instead of being 120, exactly, because if you guys think about it, it should be 120. 118 between these two molecules because we have lone pairs that are on here that cause that shift to be a little bit more, right? So if you guys think about it, if we look at the Lewis dot structure of this guy, it's really O, lone pair, lone pair. C, that's an H. Okay, so these lone pairs causes those guys to be shifted just a little bit more. So they're not quite 120. This guy is going to be 118. This guy's going to be pushed a little bit more than that. So roughly, if we had done the math, this would be like 1, 2, 1, 1, 2, 1. Okay. Make sense? Yes, no, maybe?
Kinda, yeah.
So if we have, in the case of this compound, beryllium fluoride, well, beryllium fluoride only has 2 attachments. Remember we talked about beryllium and boron being exceptions, right? So it has 2 attachments. So in this case, the bond angle between the fluoride and the fluoride is going to be 180. Okay, so they're going to try to be as far away apart as they could possibly be. Okay, does that make sense?
Yeah, kind of. You're starting to make it sense.
Starting to make sense, yeah. So it's kind of like, you know, you have 2 kids, right? You don't ever want your 2 kids that are around the same age to always be together, right? In most cases, like brothers or brothers and sisters, they kind of hate each other, right? They want to be as far away from each other as possible because if they're right next to each other, the brother's always picking on the sister, right? Like I used to do with my sister, I used to pick at her. You get, don't touch me, don't touch me. As a parent, you don't want to listen to that, right? So you want to put them as far away as possible. Does that make sense?
Yeah.
So you're not going to have them sitting right next to each other. You want to sit there and put them across the room from each other. Okay. So we're going to stop here. And so your exam is actually going to cover, it won't cover all of chapter 7. We'll, I guess, have to pick that up on the next exam, but it'll cover half of chapter 7. So you guys kind of get off on the molecular geometry.
Thank baby Jesus.
Okay. So we'll say you may get something like this on the exam, but
Dr. Henry,
don't worry. Don't
go
worry.
back a slide. Go back a slide to the easy. That one looks
this
better.
one? Okay, so we'll negotiate. I'll actually say up until this point. So we'll say up to lattice energy.
Thank God.
Okay, and then we'll save this one for the exam right before the.
Oh my God.
Okay.
I'll take that because that's more time to practice because there's
There we
too many
go.
steps.
Okay,
Ugh,
okay,
molecular
so
geometry.
I will let you guys go. You have a lab that is gonna be due next week. So you'll have a couple more days. I think it's due next Friday. I have to look again. And so it basically deals with molecular geometry. So,
Did you upload it already?
I did. I have to check. But sometimes
me
I think
check.
I upload it and it just doesn't show up. I said it's gonna
I'm
take
like,
files.
I don't think you uploaded anything, Dr. Henry.
Okay, so I have to look. I might
Yeah,
have did it.
Lab 4.
Yeah,
Yeah,
Molecular
it's
geometry?
there.
Oh,
It's there.
we're so happy. Our voice.
I can
Yes.
tell. So it's gonna take these tiles so you guys get to be happy again.
So do we have to
Okay.
show up for lab today or no?
No, no. Okay.
So that one's on our own.
Yeah, this one is pretty much on your own. If you have any problems, then you can ask me. But yeah, because it's just you're going to be cutting out the tiles and you're doing basically Lewis dot structure. So this guy is, let's say, nitrogen, right? So it has the dark ones represent the valence electrons. The white one means that it has open spots to bond. Okay.
Okay.
Okay, so the instructions are there. If you have any questions about it, you can contact me or visit me on my office hours on Thursday. So,
Baby Jesus.
okay. So I'll see you guys next week.
Monday.
Yep.
Yep.
And you'll let me know how the practice test goes
Yeah.
after it goes
Oh,
up.
so
And
the exam we have till Wednesday then, because you're giving us an extra day.
That's right.
Oh, okay.
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 All right then.
Okay.
Bye.
You guys, I'll see you guys later.